The basic idea of a propagator is that it's the vacuum expectation value of the product of two fields. Okay, that's the general rule. Now, it may be surprising, but there are many such vacuum expectation values. So I'll start first with the most basic one, which is we just put the two fields between the vacuum on both sides. We don't worry whether this is time ordered or not time ordered or anything, just put them like this. So this is a propagator. Turns out it's not physically a very useful object, that's why it doesn't have a name. But we've called it dx minus y because the physically useful ones will be linear combinations of this in some way. So the point is, this is a mathematical building block. This I can calculate and get an integral representation. Then we'll write down the physically interesting one in terms of this one. So how do I calculate this? Well, that's particularly easy. First of all, let's introduce some notation. This will be useful in what follows over and over again. Let phi plus of t and x be integral one second. Very important to get the sign correct. Phi plus has ak and e to the minus. I think in the way we wrote phi, it's the first term. And let phi minus be the other term. Okay, does this agree with what's in your notes? That the full phi is this plus this. Phi plus plus phi minus. The integral is the same, this factor is the same, and then you have a k times e to the minus ik dot x plus a dagger k times e to the plus ik dot x. This agrees with your notes? Okay, so I've just broken up phi into two pieces. So the full phi is phi plus phi minus. Now it's clear what is the physical interpretation of these two. The first one is the part of phi which destroys particles. Because ak is a destruction operator, acting on the vacuum it gives me 0, acting on any other state it removes a particle of momentum k. Of course phi is a function of x rather than k, but it's obtained by taking linear combinations over ak. So all the ak's are destruction operators. So phi plus is also a destruction operator. Some linear combination of them. Similarly, phi minus is a creation operator. Now let's look at d of x minus y. I made this comment yesterday, but let me repeat it. This quantity will not change if I make a uniform translation in all the coordinates, x mu as well as y mu. Because translations are a symmetry of the theory. And therefore, the answer for this must depend only on the difference x mu minus y. So it's only on one argument. If I had three phi's, I could move one of them, for example, to the origin, and then the other two distances would be relevant. So the answer would depend on those two. It always depends on one less than the number of arguments. Is that point clear? By translation invariance. Okay. So now what can I write? Well, using phi plus plus phi minus, in this I'll get 4 terms. But 3 of them will be 0. Which is the one that is non-zero? Yeah, tell me in terms of phi plus and phi minus. Phi plus phi minus, very good. So phi plus on the left phi minus on the right, because any other combination has either a minus on the left or a plus on the right or both. In any of those three cases, it gives me 0. So it's this. Okay. Now this thing is integral d3k upon 2 pi cubed. It's a double integral in k and k prime. I'm just inserting these things. Okay. Then e to the minus I k dot x minus y. The sign of this is important. Phi plus is x, so this is correct. And then, so this 0, none of these things is an operator, so I can take them all outside. And finally 0, a of k, a dagger of k prime, 0. Sorry, thank you. E to the minus I k dot x, e to the I k prime dot y. Correct. Now, I seem to be in a slight mess. Keeps happening. Yeah, minus I k. Okay, good. It is alright? Good. Just checking what was my original. Yeah, good. Okay, I'm okay. Very good. Now, how do we evaluate this last thing? Well, what we do is we notice that it's equal to an easier quantity, which is AK, commutator, A dagger, K. Because what I've done is subtracted a term, which is the other way. And that term, because A was on the right, is 0. And I chose it particularly to get this because this is something very easy. This is 2 pi cubed delta 3 k minus k prime. So now I can evaluate the k prime integral, and this d3k prime just sets k prime equals k. 2 pi cubed there eats up one of these. So I get this, and then the 3 momentum part of k and k prime become equal. So also the k0 part becomes equal because k0 in each of these is defined to be the corresponding omega k. So if the 3 vector k's are equal, then the omega k's are also equal. So I can write this as e to the minus I k dot x minus y, and that's the end of it. So it's that simple. This is d of x minus y. But we don't necessarily want to do it. We'll just leave it in this form. This has certain singularity properties and so on, which are not very nice. But with this, we can now turn to the quantity which is physically relevant. So we'll keep this aside. So where do we keep it? In this corner, dx minus y, which is defined as 2-point function of phi x, phi y, is d3k upon 2 pi cubed 1 by 2 omega k into the minus I k dot x minus y. That's all I need for now. Now let's turn to the Findman propagator, which is physically interesting. That is df of x minus y, and it is 0 time ordered product of phi x and phi y, where time ordering is such that the time of, so when it acts on this product, it gives me back the product of these operators, but it arranges the order the way it wants. And the way it wants is that whichever is the later time, that operator appears on the left. Okay? So if x0 is the later time, then t of this is phi x times phi y. But if y0 is the later time, then t of this is phi y times phi x. That also means that inside t, we can move things around in any order, because t, that operation of t will decide the order. So what we write inside, we can write as we like. So t of phi of x, phi of y is the same as t of phi of y, phi of x. Is that clear? Okay. Good. Now this, by definition, is theta of x0 minus y0, and then it's in this order, so we get d of x minus y, where d is that thing there. Plus theta of y0 minus x0, d of y minus x. So we see that the Findman's propagator is a linear combination of two ordinary propagators, to give, for lack of a better word for that thing, of two d's. Okay. But now, it's easy to see the formula that I gave you yesterday is correct, because yesterday I gave you a formula which said that df x minus y is equal to an integral d for k upon 2 pi to the 4th I upon k squared minus m squared e to the minus ik dot x minus y, with a prescription for the contour in k0, which says that these two poles at omega k and minus omega k, this is the k0 plane, that the contour goes below this one and above this one. So in a moment we'll just show that this is correct. That is, this, by doing the k0 integral, we'll reduce it to this form. We'll do the k0 integral twice, once when x0 is greater than y0 and once the other way. And we'll see that one time we get this and the other time we get that. So that's the proof. Actually, it's a very easy exercise. I can almost leave it to you. Does it look easy? Then I'll leave it to you. Then let's do the following exercise. Show that after doing the k0 integral, df is dx minus y if it's a very easy exercise. Okay. Of course, how you do the integral depends on taking first the choice. You have to say, okay, x0 is greater than y0. Then you can close the contour on one side. If the other thing is true, you close the contour on the other side. It all depends on how you can close the contour. And in one case you'll pick up this pole, in the other case you'll pick up this pole. And the difference is that in one case you'll get d at x minus y, the other case you'll get d of y minus x. So it's all very logical. One little comment here is that instead of having a contour like this, which is every time you write here CF, you have to say what is the contour. For example, if I took the contour to go above both poles, then it's a different propagator. It's not DF at all. Different contours will give me different answers. In fact, they are called retarded and advanced propagators. So how do we keep track of the contour prescription? An easy way is the following. Just imagine moving this diagram to the following. Supposing I could move the poles rather than the contour. I could move this pole a little bit down and this pole a little bit up. Okay, now I can have the contour going straight through the middle. It's the same as this. Because these are all tiny, so it makes no difference whether I move this a tiny amount down or the contour a tiny amount up. So it's convenient to make the poles move slightly off the real axis, and that is achieved by replacing k squared minus m squared by k squared minus m squared plus I epsilon. So I make the denominator complex. Okay, so from this I'll find that k naught is plus or minus square root of k squared plus m squared plus I epsilon. These are real. Okay, so this is the square root of a quantity which lies in the upper, sorry, excuse me, this is minus. Very good. So with the plus sign, so this is the square root of a quantity that lies in the lower half plane. So therefore it also lies in the lower half plane. So with the plus sign, the pole lies in the lower half plane. That's this one. And with the minus sign, the pole lies in the upper half plane. So exactly as I wanted. Okay? Is that clear? So therefore we can replace this contour by just writing k squared minus m squared plus I epsilon, and in books you will always see that. Okay. Now let me close this part of the discussion by writing a nice representation for the Findman propagator, which will be useful in the next lecture. So I am going to derive for you that this is also equal to this manipulation is nice because you see in this case we have not taken any expectation value. The original thing is an expectation value in the vacuum, so it's a C number, it's not an operator. Okay, but it's equal to this even though phi plus and phi minus are operators. The reason is that their commutator is a C number. Phi plus commutator with phi minus, that comes from taking AK commutator with AK dagger. And that, as we know, is some number, either 0 or 1 or something. So this commutator is a C number. So in fact, it correctly expresses a C number as a sum of C numbers. No operators here. But there is no step of taking the vacuum expectation value. Instead, you get the C number just by commutators. How do you see this? Very simple. It's a two-line argument. So we leave this also as an exercise. Since they are very easy, I think we should leave them as exercises. But I wouldn't want you to have any puzzlement about this because we are going to use it heavily in the next few lectures, next 1 or 2 lectures. So maybe let me just do this one. It will just be done in a minute. So from here, I want to derive this, right? So theta of x naught minus y naught. Now d is 0. We already saw this. Phi plus at x, phi minus at y, 0, plus the other term. I won't write the other term, I'll just show you that the first term gives you the first term. Then the second term will give you the second term. Okay, so here, this is equal to 0, is the same manipulation that we used earlier. This is equal to the same thing with the commutator because phi plus kills the state on the right. So I can always replace this by a commutator. It's exactly the same as that manipulation where we replaced AK dagger by the commutator of AK and AK dagger. Okay. But now this thing inside is a C number. So this 0, 0 is irrelevant. So I can drop it. What is the vacuum expectation value of a number? It's that number. Finished. We've got the first term. Likewise, we get the second term. Yes, strictly speaking. That's what a C number means. Okay. If you really want to think of it in language of operators, of course, it's not possible that combination of operators gives me a number, but there's a distinguished operator called the identity operator. That operator is as good or bad as a number. It doesn't do anything. It just returns whatever state it acts on. So, from that point of view, this is some number times the identity operator. 0, 0 with identity in between gives me 1. And the number part of this is what I mean when I write this. Good. Okay, now let me change gears. And also let me explain why I am changing gears. To get any further, it's very useful to describe the Lagrangian density and action for a variety of reasons. When we do field theory, just as it's very useful to use Lagrangian and action when we do particle mechanics, it's also useful in field theory. There are two reasons why it's useful. One, summarizes important information about the field, about field equations in a nice package, and makes many properties manifest. So symmetry is a very important thing, makes symmetries manifest. Of course, this is a slightly weak argument because the field equations also make the symmetries manifest, and field equations you would think are as good as Lagrangian. So this is just a weak reason. A stronger reason is Lagrangian leads to Hamiltonian, which is the starting point for operator quantization. We took a different route slightly. What we did was, instead of writing the field theory Lagrangian, we first used the field equations to get the equations of motion for the modes qk, and we wrote a Lagrangian for those modes. From that we got Hamiltonian for those modes, and we performed our quantization. But a more natural route is to start with the field theory Lagrangian and quantize the field theory Hamiltonian. Just don't refer to those modes anymore. And a third reason, which you won't see in this course, is that L itself is the starting point for path integral quantization. So these are three reasons for working with Lagrangian density and action, as opposed to just equations of motion. The equations of motion of interest to us were del mu plus m squared on phi of x equals 0. So now I claim that the Lagrangian density, which is a function of phi and del mu of phi, is a half del mu phi minus a half m squared phi squared. The Lagrangian, this is sometimes called the Lagrangian, but the true Lagrangian is d3xl, and the action is integral dt L, which is the same as integral d for x of the Lagrangian density. How does this compare with what we know already in mechanics? In mechanics, we don't have a Lagrangian density as such, okay, but we do have a Lagrangian for each mode k, and the full Lagrangian is the sum over Lagrangians for each mode k. So this is a position space analog. It's a Lagrangian for each point x, if you like. The Lagrangian for the variable phi at a given point x, then we integrate it over all x to get the total Lagrangian. And of course, total Lagrangian integrated in time is by definition the action. Therefore, the action is integral d for x of the Lagrangian density. So far, so good. Okay. Now, what is my claim? That this Lagrangian this action rather, by variational principle, reproduces this equation of motion. Okay. Let me just do one thing before I do that, which is to expand this out by using the fact that mu can be time or space. So it is half phi dot squared minus half grad phi squared minus half m squared phi squared. Okay. In this form, you can see that this is the kinetic energy T and this is the potential energy V. We know that Lagrangian is supposed to be T minus V. Okay. It's important to realize this because sometimes we think of this in field theory, we say this is the kinetic energy. Okay, or this is the kinetic term. Because of course this is relativistically invariant. So it's natural to call this a kinetic term. But kinetic actually means with respect to time evolution. Something that moves in time. So it's only this term that is truly kinetic. This term is potential in nature. Physically, you can see why. This is some variable, whatever the variable might be, its dot squared is a kinetic energy. Time derivative squared of any coordinate is a kinetic energy. Why is this a potential energy? Because this refers to the spatial variation of the field. Okay, at a fixed time, I take the gradient of the field. So if I think of the field as some kind of medium or some set of springs which are being stretched or compressed, then this is the gradient of that, the space variation. Okay, so just as a collection of springs or oscillators can contribute to potential energy by its stretching and shrinking the different directions, so can a field. And separately, the mass term of the field always contributes to potential energy. And once you realize this, you will never be confused about the signs. The signs have to be like this. Because sometimes in different conventions, this term might be plus or minus half depending on whether your Minkowski metric is plus minus 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 or minus plus plus plus. But if you are ever confused, remember that if you write it in explicitly in terms of time and space variations, it has to be T minus V. Okay. Now how do we get equations of motion out of this action? There is an extremely simple rule. We have to take S, which is the integral d for x of this Lagrangian, and we have to vary it with respect to the variable, the field variable. Exactly what we do for particles in particle mechanics. And there we say that variation of S with respect to x of t is 0. This is the principle of stationary action. So it's the same here. So we have to say that with respect to say phi of x, let's say phi of y, this is 0. Okay. So how do I perform that differentiation on this thing? This is a bit tricky. So first of all, we notice that inside here, there is not just phi but also derivatives of phi. So what is the rule that I am supposed to follow to differentiate things in phi at y? And the answer is very simple. It's not stressed very much in most books. All you need to know is that the variation of phi at x with respect to the variation of phi at a different space-time point y, what would you expect this to be? Delta. And there is nothing else you need to know. This is enough to get you the equations of motion out of this. So let's do it. Delta S by delta phi y. This is S Klein-Gordon. This is a general rule for any field. Now we are applying it to the Klein-Gordon field. So we have integral d for x. Okay. So when we act on this phi, we have half del mu delta phi x by delta phi y delta phi plus a similar term coming from varying the second one. Okay, and then here we have minus m squared, and then derivative of phi squared is 2 times phi times derivative of phi. So that 2 cancels this 2, and we have delta. So this is at x. So that's the answer. Okay, anywhere that I haven't written the argument, it's supposed to be x. Okay. Now I notice that the first two terms, these two terms are equal, because the only difference is whether the index here is up or down and here is down or up, but that I can always rearrange. So these two terms are actually equal, so I can add them and drop the half. And they are equal to del mu phi times del mu of this thing, which from here is delta for of x minus y. Now I should say what this derivative is in, just to avoid confusion, so I put a little subscript x. This was the derivative in x, because it started life that way. These are all derivatives, everything here is in x. This and minus m squared phi of x delta for x minus y. Okay. Now I use integration by parts, which tells me that this is equal to del mu in x of del mu phi delta for x minus y. That's the derivative of the whole thing, minus del mu phi of x delta for x minus y, and minus that last term. So that last term I can combine with this and write it as del mu plus m squared phi right? Now what does the first term give me? Yeah, it's a surface integral, and that's probably all I can say about it. But in field theory we normally assume that the fields go off to 0 at infinity fast enough. This is a surface integral, so this thing has to be evaluated on the 3 sphere at infinity of this 4-dimensional space-time. And we have to assume that that falls off to 0 so that we can drop this term. That assumption may not be true when we do field theories in space-times where the space has a finite extent, or when we are doing gravity or cosmology, but for this purpose it's good enough. And that term, I just evaluate integral d for x delta for x minus y, and so I get minus del mu plus m squared phi at y. What's happened is everything which depended on x because of this delta function has turned into the same thing depending on y. So everything is y here. But it doesn't matter what you call the variable. This is the answer, and it's the answer to delta S Klein-Gordon by delta phi of y. So if we set the variation to be 0, then we get the Klein-Gordon equation as desired. So that means the principle of stationary action for this action gives me Klein-Gordon equation, which says that this is the correct action. Okay, any questions about this? Yeah.
Particle classical mechanics.
It's 2, right? It's quadratic action, and that's why the equation of motion is linear in phi. So if I want an equation that's non-linear in phi, what should I do to the action? Higher order powers of phi. Good. So that immediately tells us how to think of an interacting theory. Interacting is non-linear. Non-linear means in terms of equations of motion, and all we have to do is subtract an extra term. In fact, now what we can do, is conventionally done, is to replace this whole thing by V of phi. This is called the potential. But remember, it's a field potential. This is not V of x. It's not a potential in space. It's a potential in field space. Its argument is the field itself. Okay? So, while a potential in real space might be something that drags the particle towards the origin, like V of x equals half kx squared, here it would drag the field value phi towards the origin, or towards whatever is the minimum of V of phi. Okay? And in that language which I showed you earlier, the full potential energy of this, or the full potential energy is grad phi squared plus whatever is this V of phi. This is in our hands and this is always there. Okay. Now, what can V of phi be? Pretty much anything at this level. So, any kind of nonlinear, any function you like. Can be a polynomial, can be an exponential. But supposing we think of very simple examples. So, constant is no good, because constant, anyway, it contributes nothing to the equations of motion, and it in the Hamiltonian, which will be pi dot minus L, it will contribute an additive constant to the energy. So we are already throwing away lots of additive constants, so it's no good. Linear in phi is also no good, because if I have a linear term in this, then by shifting phi, I can remove it. Is that clear? If I have, for example, a phi plus m squared phi squared, then phi goes to phi plus some constant, sends this above thing to just half m squared phi squared. Shifting phi by a constant removes a linear term. It may also add an overall constant, but that anyway we are dropping. So linear is also no good. Quadratic is always there unless the theory is massless, which is a very special case. So whatever is the quadratic term, we always take it to be half m squared phi squared. That we already took in the free theory. Okay? So that leaves things like cubic and quartic. And in principle higher order. But we'll see that there's a restriction that this kind of field theories make sense only if the potential is at most quartic. Okay? That restriction is called renormalizability, which we'll mention briefly towards the end of this course. Okay? Is the restriction that the quantum theory should be consistent. It turns out that in field theory, not every interacting field theory we write down can be consistently quantized, and so the restriction on powers is very strong, that we should have only at most quartic powers. So it means that the most general potential we will be interested in is this plus cubic plus quartic, but I'll also drop the cubic one because it doesn't add very much information, and I'll only have the quartic term, and I'll give it an arbitrary coefficient which I'll call lambda, and it's not conventionally normalized by perfactorial. Just simplifies some formula. And this version of Klein-Gordon theory interacting via this potential is just known as phi to the fourth theory, and we'll study it in the rest of today and the next. So to summarize, the interacting Klein-Gordon theory of interest will have this term, this mass term, up to here this is the free theory, and this new term which is quartic. Therefore in the equation of motion it will be cubic, so it's a non-linear equation of motion, and this is an interacting theory. We'll see that this theory describes particles which not only propagate but also interact, and it's not hard to guess that lambda will be the strength of the interaction or the coupling constant. After all, if lambda is 0, then there is no interaction. So it's reasonable that the more strong we make lambda, the larger we make lambda, the more there will be an interaction.
Why didn't we take
Why what?
Why didn't we take 5 raised to
Why didn't we take? Just for simplicity. We could have. Everything I say will go through with phi 3 also. However, there's an important point. Phi 3 alone without phi 4 has a problem. Can you see what it is?
If we take the x going to minus x, then phi cube will make a problem.
Yeah, it will violate some symmetry, but we don't have to have that symmetry. But just think of a particle. Just think of an ordinary particle moving in a potential v of x. Okay, so half x dot squared minus v of x. Okay, now let's compare v of x equals x cubed and v of x equals x to the fourth. Yeah, so x to the fourth goes steeply like this, but x to the 3 has this kind of form. So it's unbounded below. That means that dynamically in this case the particle will like to go to x equals minus infinity to minimize its energy. So the energy is bottomless, so the system just runs away. Doesn't have any consistent stable behavior. Exactly the same will happen in this case. If I have phi 3 alone, the value of the field phi will try to run away to minus infinity. If I have phi to the 3 and phi to the 4, there is no problem, just as here. If you take x to the 3 plus x to the 4, you get some asymmetric potential. It might be like this, but it's still bounded, because after all, for large enough x, this term always wins, and this term is always positive. Is that clear?
So this will again get back the negative energy problem.
Not the negative energy problem, well, it is actually a kind of negative energy problem, but it's not related to the previous negative energy problem, because, one second, this is a negative energy problem just in the classical theory. Doesn't have anything to do with quantum mechanics. You can't observe both the linear and the cubic term. And in fact, it's genuine, it's quite genuine because it violates the symmetry phi goes to minus phi, and nobody says that symmetry has to be there. Let me also say at this point that if this was a field theory describing some particle in the real world, then experiment would tell us what potential to have, whether phi 3 plus phi 4 or phi 4 alone, and with what coefficient. But right now we are doing a model field theory, which we are not trying to use it to describe any particle in the real world. So for that, we just take the simplest possibility. Later, when we do more realistic ones, we'll see that experiment fixes what these interaction terms are. Okay. Before going on, I want to say a few words about dimensions, which is very useful. You see, the action is integral d for x. Let me write now the action we are working with. Now, do you know in quantum mechanics what are the dimensions of action? Sorry.
Dimensions of angular momentum.
Dimensions of angular momentum. Very good. That's correct. So it's the same as the dimension of h bar. H bar has dimensions of angular momentum. In fact, angular momentum is quantized in units of h bar. So S in fact has dimensions of h bar, and in the path integral approach to quantum mechanics, if you have studied that, the basic object is e to the I times S upon h bar. That is the basic object from which you start defining the path integral. Okay. Now in our case, h bar has been set equal to 1, so S should be dimensionless. Moreover, since C is 1, C equals 1 implies that length dimension and time dimension are the same. Good. Now let's look at the first term and try to find out from it what is the dimension of phi. Okay. You see that this has 4 powers of length, but there are two derivatives, they have minus 1 power of length each because d by dx. So total 2. So phi has dimensions minus 2 in units of length. Okay. Or plus 2 in units of energy, which is inverse of the unit of length. So I'm going to write that dimension of phi is plus 2 in energy units. In energy units, length and time have dimension minus 1. Okay, and that's all we need to know. Okay? Sorry, plus 1. I meant to say plus 1. Sorry, I wrote plus 2. So plus 1, then del of course has dimension plus 1 in energy units, because we know del is a representation of energy or momentum. So plus 1, so this is 4, that's minus 4, so that's good. What about the second term? That should be consistent. M should have dimension plus 1 in energy units because mass and energy are the same thing. Okay, so 2 again and 2 from this, so we are fine. Okay, what about the last term? So we learned that lambda is dimensionless. Okay, in the same units. Notice that if we went to different space-time dimensionalities like 3 dimensions or 6 dimensions or something, then all these will change. So the character of field theory changes importantly from dimension to dimension. We always work in 4 dimensions, but condensed matter physicists, for example, apply these techniques sometimes to 3-dimensional or 2-dimensional systems. So they have different scaling behavior of their fields. Okay, now supposing I had a phi to the 5th or phi to the 6th interaction, what would be the dimension of the constant in front of that? Negative. Okay. So therefore, the fact that we are allowed maximum quartic is the same as saying we don't have any coupling constants of negative dimension. So we'll make this a rule, no coupling constants of negative dimension. And this rule comes from consistency, or as it's technically called, renormalizability of the quantum field theory. And just to say again in one line what that means, you see, nothing can stop us writing S of phi for any v of phi that we feel like, phi to the 6 or 10 or 100 or d to the phi. Classical field theory you can always write. But making a quantum theory out of this is extremely subtle, and at various stages one encounters problems which one has to fix, and those problems turn out to be unfixable, cannot be fixed if there are any negative dimension coupling constants in the theory. Okay. So we'll come back to this point towards the end of this course, but you just can remember it as a guideline that there should never be coupling constants of negative dimension. Okay. This doesn't rule out phi to the 3. In phi to the 3, the coupling constant would have dimension plus 1, and that's perfectly alright. So there's nothing wrong with phi to the 3, but there is something wrong with phi to the 5 or 6 or 7. Good. Okay. What about the Hamiltonian? So corresponding to the Lagrangian density, there is a Hamiltonian density written as script h. For that, first we take the Lagrangian and differentiate it with respect to phi dot. This is how we would have found the canonical momentum of a particle in particle mechanics. So whatever we get, we'll call it phi of x. We have already encountered phi of x in the last lecture, but this is the in-principle definition via the Lagrangian density. Next we take phi of x, phi dot of x, minus L, and we call this h, but in h we replace all phi dots in terms of pi's, so that h finally depends only on pi and phi but not on phi dot anymore. And if we carry out that procedure here, we find the answer to be half pi squared plus half m squared pi squared, or more generally plus v of phi, well, plus half grad phi squared plus v of phi. So what happens is that this procedure of calculating pi and writing pi dot minus L, it really acts only on the phi dot squared term of all this. Everything else is potential with a minus sign in the Lagrangian. So it comes back as potential with a plus sign in the Hamiltonian. Hamiltonian is t plus v. So everything is clear. This is the potential. So that includes the field potential which I put by hand and the field potential which comes from space variation of the field. Both are part of the Hamiltonian. This is the Hamiltonian density. So its physical interpretation is the energy density in space. So the Hamiltonian, which is the operator of energy, is d3x h, just as one would expect. So now that we've got all this, let's focus on the theory of interest to us, the pi-4 theory. And for it, the Hamiltonian is half pi squared plus half grad phi squared plus lambda by 4 factorial, plus half m squared phi squared plus lambda by 4 factorial phi to the 4th. So what's our goal? This is a theory. We would like to know the eigenfunctions and eigenvalues of this Hamiltonian, for example. Or in more practical terms, we would like to know if the particles that we already studied arising from the free part of the Hamiltonian, this much, we would like to know whether that last term makes them interact, and if so, how exactly. We would like some formulae for the interaction of those particles. Right? So that's the goal. So surely if we could diagonalize this Hamiltonian in some way, then we'd be done. We could know everything we want about this system, just as we effectively diagonalized the first part in the last couple of lectures. What did we do? We were able to rewrite the whole first part as summation omega k ak dagger ak. And from that we could deduce the entire particle spectrum of the theory. So if we could do the same, but with the last term, then we would be through. But unfortunately we can't. So we cannot diagonalize this exactly. Or just say cannot solve exactly. So nobody has been able up to now to solve such a simple looking system exactly, and that's the reason why we need to do a lot of work to extract physical consequences from this. So one approach, it's not the only approach, but it's by far the most successful approach over a long time, is to break the Hamiltonian into two pieces and call this H0 and this H interaction. So h is h0 plus h int. Okay. And assume lambda is much less than 1. Lambda is a dimensionless constant governing the interaction. So we assume it's less than 1 and use perturbation theory in lambda, in powers of lambda. As soon as we say this, you can start imagining what kind of picture is going to emerge, and it's good to imagine that before we actually do the calculation, because the calculations are a little bit tedious and sometimes ugly, but the physical picture is very clear. What does it mean in a field theory to have perturbation theory in powers of lambda? It means that for any physical quantity, there will be a contribution from the theory where lambda is set equal to 0, then a first correction to that proportional to lambda, then the next correction proportional to lambda squared, and so on. Right? So everything will be given order by order in lambda. Now what is 0th order in lambda? That is what we've been discussing for the last 3 days. Okay, because the theory we've been discussing for the last 3 days is this theory without lambda. Okay, so in that theory, there are free particles of arbitrary 4 momentum or arbitrary 3 momentum k and energy omega k. As many as I like. There are states with few particles, many particles, no particles, all those states are there. But none of them exhibits any transition into any other state because they are all free. Okay. Now, what would be the first correction? So, for example, in such a theory, there would be no scattering. Let's think of a picture. Imagine 2 incident particles. So, this state I could prepare in the free theory. A state with 2 incident particles of 3 momentum k1 and k2. Now, as long as lambda is 0, what is the possibility for time evolution of this state? What can it become far in the future? The same state exactly. This particle keeps propagating and this particle keeps propagating. So, the outgoing particles also have momentum k1 and k2, and in all respects they are identical to the incoming particles. That's what you can do when you don't have lambda. Okay? But now, it's a slight reinterpretation. This is like the order 0 contribution to something which will have corrections. Now lambda is non-zero, but this is still the leading contribution. That means that the leading behavior of 2 particles which are sent in to a system which has a small lambda is that they won't do anything and they'll go out. Okay? So that we must accept that in a weakly coupled system, particles have the option to do nothing. Okay? But they also have more options. And the question is, what are those options physically? So, to first order in lambda, what option do we expect? The best guess is that they'll scatter once. Okay? Because every scattering process should cost you an amount lambda, because lambda is the parameter of the interaction. Okay? So, in some sense, which we'll make precise later, the particle should scatter once. So, you can imagine a picture like this. And if they scatter, then there is no reason why the outgoing particle should have the same momentum. You could even argue there is no reason why the outgoing particles should be 2 in number. Actually, even that's true. Once they scatter, they may create any number of particles and 4 may go out, or 10 or 100. Is this what happens in real life? In real life accelerators, when 2 particles scatter, do they give out dozens of particles? Yes, very good. Everybody looked very doubtful because I phrased the question that way, but that's exactly what happens. An accelerator is a place where incredible mess of particles comes out even if 2 particles go in. Okay, now the current accelerator LHC already sends in an incredible mess because it sends in protons. But the older accelerator LEP had electron and positron, just two particles, just two perfectly fundamental particles. But at the end, all kinds of things came out. So it's not just that simple, it can be anything. Even so, one might expect that for sufficiently small value of lambda, just one scattering, you might expect that a small number of particles will come out, and they will also have small changes with respect to the particles inside, the particles coming into the experiment. So this sets up a physical picture of what to expect, that with this term there will be some scattering, but there will be some lowest order, next order scattering, and we can catalog all of those, and those will all, because this is a quantum system, they will all be related to some probability to produce some particles in the final state. Okay, and because this is a system without a fixed number of particles, unless we know some more details, we can't say how many particles will be produced in the final state. Okay, so this is a general physical picture, and now we have to justify it by doing calculations with this Hamiltonian.
So you said lambda density interaction strength.
Yes, yes.
So how can you choose lambda? Shouldn't lambda be dictated by nature?
Yes, yes. When I say we choose it, I mean the following. Lambda. Okay. So this is a toy theory. Okay, and what we do is that we try to solve it as a function of lambda, but assuming lambda is small. At the end, the answers are all dependent on lambda. If this was a theory describing nature, then nature will fix the value of lambda. As an example, when we generalize this to electrodynamics, there will be an analog of lambda which couples electron, positron and photon. That will be called E. That's because it is the electric charge of the electron, which is determined by nature. So it's the analog of that. But even in electrodynamics, what the attitude we take is to solve the theory or study the theory as a function of the parameter E. Only at the very end, when we get our answer, then we put E equals whatever it is and evaluate it and get a number and compare that number with experiment. Okay? Good.
This comparison is possible if your answer in the parameter is a convergent series of
Thank you. Thank you. So the question is, we are going to do a power series in lambda, and question is that does this power series converge? Okay, and it turns out to be an extraordinarily difficult thing to achieve. In fact, to our knowledge, any of the field theories we study have power series which do not converge. Okay, but they satisfy some weaker condition, which is that they are asymptotic, which means that up to high enough orders, you get closer and closer to some answer, and then after some sufficiently high orders, they diverge again. Okay. Now there's a whole study of that, and it's important. It also has to do with questions like whether the field theory is asymptotically free or not. Many important things. But just to let out a secret, we'll never use more than small number of powers of lambda for any practical considerations involving comparison with experiment in electrodynamics, for example. Okay, first order, second order, third, fourth. There are people who have gone to sixth or eighth order using computers, but we are still around there. So the question of what happens at 100th or 1000th order is, for practical purposes, need not worry us. Actually, in this course, if we understand things to first order, that will already be very good. You know that in your quantum mechanics course, you know that first order perturbation theory is sort of easy, and then second order onwards it becomes more and more complicated. Here the complication grows enormously. We'll see some examples how it grows enormously. Okay. Now remember that in free theory, from now on, whenever I say free theory, I mean the theory with Hamiltonian H0. The vacuum state 0 satisfied non-zero to 0. To be fair, this was achieved after removing that infinite constant in H0. So at the end, H0 was just summation omega k, a dagger k, ak. So obviously it kills the state. So this is the definition of the state. And all other states have positive energy with respect to this. Now in the interacting theory, this theory will also have a vacuum. This is the theory with Hamiltonian H. By the way, now I perhaps I should say H, and I don't want to work with the density anymore. Yeah. So in the interacting theory with Hamiltonian H, there will also be a vacuum, and in fact now we should only work with that vacuum. We are not interested in the free theory anymore. But because we are doing perturbation theory around the free theory, we want to keep the free theory quantities as well as the interacting theory quantities, because the interacting ones will be expressed in terms of the free ones. So therefore we give a new name. The vacuum is called omega, and it's defined by H omega, which is the same as H naught plus H int omega, is minimum. Let's say it's minimum. Of course, it should be an eigen state, so some minimum energy times omega. Right now we won't worry if that minimum energy is 0 or not. The point though is that the defining equation for this and for 0 are different. This is defined in terms of H0 and this is defined in terms of the full H. So what can we imagine? We can imagine that we have a system which has no interaction, lambda is 0, and the system is in the vacuum. Now imagine slowly turning on lambda. The nature of the vacuum will change because it's a new equation. It will satisfy this. The vacuum will evolve from 0 to omega. Okay. Now omega cannot be the original vacuum. Can we be sure about that? There's a simple way to be sure about that. Look at H interaction. It goes like phi to the 4th, right? And phi to the 4th, this is the same as phi plus phi minus to the 4th. Okay? In the language of free fields, this thing has many terms, including, for example, phi minus to the 4th, phi plus times phi minus cube, all the possible terms, right? Now this term is certainly going to create a lot of particles from the vacuum, 4 particles to be precise, because it contains 4 A daggers. Okay, that means that the old vacuum, the free vacuum, cannot be the vacuum of the new theory, because the interaction term creates particles from that vacuum. Okay, so you must change the state in some way to compensate such that finally there are no particles in the interacting theory in the new vacuum. So is that sort of clear? Again, there is some analog if you look at your quantum mechanics text when you do perturbation theory. The Hamiltonian changes, the energy eigenstates also change. You in fact learned how to compute those. Both the eigenstates and the eigenvalues change. In particular, the ground state changes.
Sir,
yes.
Is there any law which will govern this evolution of data and how 0 will...
That's what we have to find out. That's in fact the job. Perturbation theory that we are going to do is going to help us to find omega. We have to find it. When you say, is there any law, what do you mean?
I mean, like the operator evolves in the type AKT equals to 0 minus IH.
No, that operator evolution is in free theory. This is when I said evolve here, I mean something very different from what you mean. In free theory, an operator in the Heisenberg representation evolves with time. Okay. Here what I am saying is, when we turn on the interaction, The vacuum state, even at a fixed time, evolves into a different vacuum state. You shouldn't think of this as time evolution. This is just one state turning into another state. I think if you go back to your field, to your quantum mechanics text, you'll find everything is done, everything is said there. Okay? The ground state, take a harmonic oscillator, just think of this problem and model it with something that you already know. What do you already know? You know the Hamiltonian p squared by 2m plus half kx squared, and add lambda x to the fourth to it. What is that? Anharmonic oscillator. Okay? Now in anharmonic oscillator, are the energy levels equally spaced? No. Is the ground state energy half h bar omega? No. Is the ground state the state annihilated by A dagger? No. By A? No, it's not. All of these facts change by a small amount proportional to lambda. Okay? So one exercise you may want to do now or this afternoon or when you go home after this school is to work out the anharmonic oscillator and think through all the concepts over there. What happens by turning on the x to the fourth perturbation? Whatever it is, it will be similar here but much harder because this is field theory. Conceptually it's the same idea. Okay?
Instead of treating time as a parameter, treat lambda as a parameter in this case.
Yeah, but it's not instead of treating time. Time evolution will be there still. Time evolution is not going away. Okay? But if you like, yes, we are saying that when you turn lambda, as lambda varies from 0 to some finite value, the state evolves. If you want to think of that as a parameter, yeah, you can.
So, can we say that when we talk about interacting field theories, the notion of vacuum state is like, there's no vacuum state?
No, there is a vacuum state, omega. This is the vacuum. That is particles in terms of the free theory. It's empty in the interacting theory, by definition. But if you expand that vacuum state in terms of the free theory, then it has particles. That is the funny thing. The point is, if you could diagonalize the interacting Hamiltonian, then your definition of particle would be whatever states the interacting Hamiltonian has. And then the vacuum should have nothing. But because of this crutch that we always use, that H is expressed in terms of H0 and H int, this expression is, I am expressing the interaction Hamiltonian in terms of the free field. So in that language, in terms of free particles, yes, the vacuum is full of free particles.
Whatever is the particle for this zero vacuum state may not be particle for omega vacuum state.
That's right. But because we are using perturbation theory, the concept of free particle is still retained. And the reason I think you can see in this picture, in a truly free theory, particles just propagate without interacting. But in first order in lambda, they can only interact once, which means for most of their life they are still free. You see, what happens here is that here something happens with strength lambda, but from infinity up to that point the particle has to propagate freely. Because if it doesn't, what happens? Supposing it interacts on the way, then I get another power of lambda. Then it's not the lowest order term, it's the next order term. Okay, so that means that if I'm concentrating on low powers of lambda, then it means that particles on average have no interactions except once in a while. Small number of interactions. That means that for the most part of their life as quantum particles, they are free particles described by H0. That's exactly what it means to split H0 plus H int. This acts few times, but this is always there. This, by the way, is consistent with our picture of the world, right? If you take a chamber and evacuate all the air so that it's got vacuum in it, I think it's our common sense that we don't see a lot of things bubbling and happening there. Why? Because it's actually the theory that we are working with is weakly coupled. And for the most part, free particles just behave free. Okay. Good. Now, because of this, not only is the Hamiltonian broken into two parts, but we are also led to think about two types of fields in the theory. And the way we think about it is the following. Suppose at some time t equals 0, we have a field configuration phi of 0 and x. And now supposing we want to study its time evolution. This is in this interacting theory. We can define phi 0 of t and x to be e to the ih 0 t phi 0 phi of 0 and x. So this is the field evolving according to the free Hamiltonian we wrote down an expression for this field yesterday, but we can also define phi of t and x, which is e to the I times full Hamiltonian so this is field that evolves according to the full Hamiltonian. Now you might argue that the first thing is absurd because there is no such field in my theory. That's true, right? The only field in my theory is the one which evolves with the true Hamiltonian H. There isn't any field which evolves with the free Hamiltonian H naught. However, one should realize that the field is not an experimental observable. It's just something that we use in our calculations. So therefore, by keeping both of these, if it helps me do my perturbation theory, then I can take this as a tool. So what I'll do is, at all times I'll keep this field and this field, and we'll set up our perturbation theory using both of them, and we'll see exactly how the physical quantities expressed in terms of this get rewritten in terms of this. So the goal here is to express the interacting theory in terms of variables of the free theory. So let's write that goal. Express physical quantities of the interacting theory in terms of the free theory. And this we can nicely make concrete by saying the following. What would be a simple physical quantity of the interacting theory? It would be the full propagator, the interacting propagator. Okay, what should that be? That should be the amplitude for the particle to propagate from point x at time x naught to a point y at a later time y naught. Okay, but not in the free theory, in the interacting theory. So the full propagator or interacting propagator by definition, what should I write for it? Can you tell me what I should write? What expectation value? Omega. So it should be in the vacuum omega at both ends. Okay. And what should appear here is the time ordered product of phi x and phi y, where phi x is this one. If it has no subscript, then it's the full field. This is what I want. Okay. So if I could find the answer for this without any calculation, then I don't need this. Instead of that, what we are going to find is that this is equal to 0, some complicated function of phi 0, function of many phi zeros, there will still be time ordering here. This is our kind of goal, because once we get this, then this is a calculation in free theory between the free vacuum and the freely evolving field. So this is the goal. To make the goal more precise, we can even start with this. In perturbation theory, what can this be? In perturbation theory, the first term has to be this. We don't need any calculation to tell us that, because the first term for any expression in the interacting theory is the corresponding expression in free theory because the interaction is turned off. That's the leading term. It's the only term which survives when lambda is put equal to 0. Therefore, the next term must be lambda times something plus lambda squared times. And right now, with our present level of knowledge, we can't say what these things are going to be. Okay? But the only promise is that they will turn out to depend only on phi 0. Okay? So can you see that this is the most reasonable thing that we can expect? First term anyway we know for sure. Other term has to be of order lambda. Okay. Now once it's of order lambda, if there was any interacting field here, then that field would have a lambda dependence. Okay. So, but then I can set lambda equals 0 inside because I've already taken lambda out. So that means that the field inside must be the free field. This is sort of the logic. And this is logic for any perturbation theory. It doesn't have to be field theory, quantum mechanics or any system. That is, at each order, once you have established what is the constant dependence, then the quantities in the calculation will all be free quantities, unperturbed quantities. So this is the structure. So this is our goal. Yes?
Sir, it is okay, perfectly okay that when we are switching off the interaction field, then it is that should be 0, t, time order and another 0.
Yes.
But sir, when we are knowing the concept of interaction feature,
Yeah.
the lambda,
Yeah.
then the vacuum state is also then 0 or there should be omega?
The vacuum state is omega. That's on the left side.
Yes, sir.
Okay. This term comes from the fact that see, you have to be very clear what is the meaning of the two sides. The correct side is here. This vacuum depends on lambda. These fields depend on lambda. Everything depends on lambda. Now I am expanding in lambda, powers of lambda. So the first term is I put lambda equals 0 there, so I get this. Now next term, let's say I take the first order change in this vacuum. Okay, so the vacuum is omega is 0 plus lambda times some other state. Okay, but that other state I can express as 0 times some operators, some free operators. Because all states in the free theory are built above the vacuum using operators. So that is all incorporated in this. That's why what is coming inside this is not just 2 operators. This could be 4 or 10 or 100 operators. And how they are combined in here we don't know. What we know is that they must be all free field operators. Their job, among other things, is to convert this vacuum to this to first order in lambda. Is that clear? Okay. Actually tells me how phi is related to phi 0. Phi of t and x is written like this, but phi 0 can be solved from the first one in terms of, so phi at t equals 0 can be solved in terms of phi naught, just by inverting the upper relation. So I have the relation that this is e to the I h t e to the minus I h naught t phi 0 e to the I h naught t, right? So this tells me at any time t the relation between the interacting field and the free field. Now, what can we say about this combination e to the IHT, e to the minus IH naught t? It looks like it depends only on the interaction part, because h minus h naught is h int. But unfortunately it's not so. This is not equal to e to the I h minus h naught t. If it was equal, that would be wonderful, because then we would have a clear relation involving only the interaction Hamiltonian between this and that. Why is it not so? They are operators and they don't commute, in fact. One way to see that they don't commute is that if, okay, so h and h naught commutator is the same as h int and h naught commutator, because so h with h naught is equal to h naught plus h int with h naught. So first term of course is 0. So it's h interaction with h0. Now you can easily convince yourself, just pick one of the terms in h interaction in terms of the oscillators, a dagger to the fourth. Okay? Does a dagger to the fourth commute with a dagger a? No. End of the story. This is of the form a dagger a. And this is of the form a dagger to the fourth, a dagger to the 3 times a, etc., etc. So you can see that generically they just don't commute. Therefore, this is not true. Therefore, it's convenient to define an operator which will play a fundamental role in what follows. U of t is defined to be whatever appears here, and then U governs the relation between phi and phi naught by U inverse phi naught U, all at time t. Correct? And of course, and U is unitary, so U inverse is the same as U dagger. Is it clear that U is unitary? If I take U dagger, I get this stuff and that stuff is 1, without assuming anything about commutations. Okay. Good. So I'll give you something to puzzle over till tomorrow. Well, let me not give you anything to puzzle over till tomorrow. I'll stop here. Okay, and tomorrow we will study time evolution of U of t, the time dependence of U of t. Of course, it's explicit here, but the problem is I can't think of this in terms of h interaction for the reason I already told you, that this is not e to the I h naught minus h t, but I can think of it in terms of powers of that. That is, to leading order it is e to the I h interaction t, and then there are many corrections. Okay, so using that I can study the time dependence of U of t order by order in the interaction, and this will be a tool to allow us to achieve this final goal, which we'll do next time, which I think means Monday. Okay.